It's nice to think of the tides being important for sailing by virtue of the fact that they bring the water closer to you, and you don't have to hold your dinghy over the mud, as is the case here with this illustration of Skerries. And
Oh, it's a
it also
jinx.
means that your cruiser, if you have a small bilkeeler on an inner mooring, doesn't get dried out. This cruiser, you get to go sailing. But the tide for sailing is much more important than that. It's much more than a convenience. It has an awful lot to do with how we sail, where we sail, and indeed how fast we sail. There is, I suppose, a lot of innocence where people might think that somehow or another the tide just surges in from somewhere out there in the middle of the Irish Sea, and a little bit of water comes in and brightens up our dull little lives. But in fact, it's much more profound than that. And in fact, it's one of the most amazing things that nature throws up several times a day. The tides don't come from the a bit out there in the sea. They actually come from the Atlantic, helped by the agency of the moon and the sun, which by their gravitational pull raises an enormous mound of water out of the horizontal, as it were, probably up to about 1 meter high in the mid-Atlantic, or in the various places where the tides kind of begin, and there are several of them. There's a word that I cannot pronounce which describes them, and the experts will fill you with dread talking about them. But this mound of water flows towards us, and it encounters the Bristol, or it encounters St. George's Channels, the western approaches, and then between Ireland and the tip of Cornwall, it's funneled into the Irish Sea. And this has the effect of raising the height of what started off as a 1 meter, 40-inch mound of water into a surge of water that can be upwards of 14 feet high. So it is magnified more than 4 meters. The highest tides we get are about 4.5 meters. So work that out in pounds, shillings, and pence, and you'll realize it's quite a lot. And you can see the harbor over there. The pier is, the water is, there's only a few inches of water at the base of the pier there, but you can see the height of it between the water level and the top of the pier. Sometimes, it doesn't happen very often, I've only seen it once myself, water actually comes over the top of the pier on a very, very high tide. Sometimes it's helped by a storm surge, sometimes not. And it's known as the highest astronomical tide, and by golly, is it high. So on its way to us, and then it goes out again, of course, and that surge of water reverses direction and heads back down the Irish Sea, spews back out the St. George's Channel and the western approaches, past the south of Ireland and back into the Atlantic again. It's an enormous undertaking for nature. And if you work out how heavy water is, and think of the weight of a meter of water, say a square meter of water, you are talking about tons. And then work that out, spread that, find out how many square meters a meter deep, or several meter deeps there are in Skerries Bay alone. And you were talking about an incredible amount of water, an incredible weight of water, which is surging up and down the Irish Sea twice a day. And in fact, it's no exaggeration to refer to the Irish Sea as a river that changes direction twice a day. It's the water flows in and the water flows out again. And in flowing, it generates a current. Now, not a very fast current. We've seen faster currents on streams and in rivers and that sort of thing. But the mightiness of this current, it is all pervasive. It extends right across the Irish Sea. It's faster around headlands and through, in between islands and the mainland. And It's slower in big bays. So it's quite a thing, and it can make or break your day when it comes to sailing, because if the tide is against you when you're sailing from A to B, you're going to be slowed down. You're probably lucky to be sailing at a rate of 4, 5, maybe 6 knots, depending on the size of boat and the types of sails you have up. But if you are sailing into a 2-knot tide, which you can experience at very, very high tides, it's going to reduce your speed by between 30 and 50%, depending on the speed of your boat. So the corollary, of course, is true. If the tide is going in the same direction as you are, it's going to speed you up. Happy days. Races are won and lost on the tides. And I'll give you a very good example. Every year we have a very, very popular race we call it the Rock Race. In fact, it's the Tommy Rooney Trophy. And it's a race from Skerries out to Rockabill, the lighthouse that you can all see on the horizon out there. Around the rock, you go around it clockwise, yeah. So you go around the back of the rock, come right around and race back again. That is a race that is won and lost, not so much on the speed of your boat, but on how you judge the tides. These guys, if they are sailing to Rockabill, and I don't think they actually are in this case, I think they are in a local race and they're racing to a buoy not too far out. But if they were racing to Rockabill and maintaining that particular course, which appears to have them heading straight for the rock, and they keep that course, they're going to be sorely disappointed, because they're going to end up way down here off the screen if the tide is falling. If the tide is filling, in other words, this surge of water is rushing up the Irish Sea, trillions of tons of it, it's going to push them this way. And if they keep that course without altering it, they're going to end up somewhere off Balbriggan. So it's judging the tides, judging the strength of the tide, and working out how you can angle your boat, either if the tide is falling to head up this way, or if the tide is rising to head into it a bit and try and get to the rock, be swept down to the rock just as it's time to go around it. Carefully judged maneuvers. A lot depends on the time that you do it, because the tide goes at a different speed at various times during its cycle, and I'll go into that in a minute. It also depends on the strength of the tide, and there are different heights of tide. And I think we'll go and have a look at that now. You've probably heard of spring tides. We hear about 2 different types of tide. You'll often hear about spring tides, and the more innocent among us might assume that they're tides that occur in February, March, April, maybe into May. Not at all. They occur twice every month of the year, and they are the highest tides, generally speaking, of the month. Then you have other types of tides. You mightn't have heard too much about them, and they are neap tides. And neap tides are, well, they're the lowest tides of the year. And that's a bit incorrect, because they have the lowest high water, the lowest high water, and the highest low water. In other words, the range between the tides is not all that great. So if you have a spring tide, and we'll just write SPR, and let's take Skerries Pier as our reference point. And let's say this is the top of Skerries Pier. And this is the wall. And this is the mud at the bottom, right? So a high spring tide, and there can be various heights of spring tide, but let's assume we've got this one that I talked about earlier, which came right up to the top of the wall and spilled over. So that's high water spring, H W S. That's high water spring. Low water spring is way down here. It's the tide has gone out so far. The mud doesn't account for it. So, but let's assume that's where it is. It's there. Low water spring, and we just do LWS here. So this is an enormous tide. Trillions and billions of tons of water have come up the Irish Sea just to fill up Skerries Harbour. And make that into a little arrow. And that when the tide is in full, it comes up to here. When the tide is in low, or when it's gone out, it's there, right? And this can last over several days. And generally then the tides, the amplitude of the tides will decrease. And when I say the amplitude, the distance between this HWS mark and this LWS mark will shrink, right? And you get to neaps at between high springs, you get neaps. And high water neaps could be here. So you have two different high waters, and low water neaps is here. So let's just label those. L, no, that's H, isn't it? Let's do an awkward H. I got away with that. And that's high water neap and low water neap. Okay, so I'm very pleased with that. So the amplitude of the neap tides is from here to here. And the amplitude of the spring tides is from here to here. So when I say the neaps shrink in amplitude, that's exactly what they do. There's just that much, whereas the springs can be enormous. The entire harbour will dry out. I have seen the very end of the pier dried out. You don't see it very often, but I have seen it. And I've been able to walk around the end of the pier without hardly getting my feet wet. The neaps, on the other hand, they don't go out, they don't come in too far, they just come up sometimes over a little bit further than the end of the slipway, halfway up the slipway max. But the lovely thing about the neaps when it comes to dinghy sailing is they don't go out very far either. So they'll be just a few yards off the end of the slipway, and you'll be able to get your boat in and out fairly easily. Springs, on the other hand, you've got to drag your boat all the way to the end of the pier sometimes, as we saw in that photograph earlier. Now, so twice a month, you're going to have neaps. Twice a month, you're going to have springs. They're roughly equidistant in time. And we'll have a look in a minute at what exactly causes it for the more curious among you. But the thing to remember, and let's go think again of those mermaids racing out towards Rockabill, is that if it is a time of spring tides when they go sailing out to Rockabill, they are going to find the tide stronger. If it's neap tides, the tides will be weaker. So they don't have to be 100% correct in the allowance that they make for the tides. They can fudge it a little. So they might in some sections be only half the strength, the current, the flow of the tide, maybe only half as strong as a very, very strong spring tide, a very high spring tide. And spring tides get even higher around the time of the equinoxes. And it would have been around then that I would have seen the water lapping over the top of the pier around an equinox. Equinoxes occur in, isn't it, March and September. So that's why it's important if you're, for your navigation or for your racing tactics or for a million other reasons to know about the difference between springs and neaps and the impact it can have on your sailing. Low water springs, for example, even in the smallest dinghy, at low water springs, you're not going to get through the sound between Shennick Island and the South Beach. No way. It'll be just mud and sand all the way. Low water neaps, on the other hand, there'll be a fairly good trickle of water still there. And you'll be able to, on a very small dinghy now, you'll be able to manage to get through um, uh, on the landward side of Shannick Island. High water springs, you'll always get through. High water neaps, you'll always get through. But the low water sections make quite a difference. So you'll be able to do a lot, get a lot closer to the land at low water neaps. Low water springs, forget it. You're going to be hitting rocks and bouncing off boulders all over the place. So
does the duration, Jerry?
Go ahead.
Can you hear me?
Yeah.
Yeah.
Does the duration of the tide time change between spring tide and neap tide?
No.
Or it's just the flow is different level, different speed?
And that's actually a very good point you've raised.
Yeah.
Because that's another explanation why the currents and the strength of the tides, the currents that they generate, can be almost exponentially stronger, because all that extra water that flows into the Irish Sea to give us a high water spring tide has to get out again in exactly the same time as, shall we say, it takes for a neap tide. In other words, a tide of much lower amplitude. There's only this much water has come in, as opposed to this much water for a spring tide. And yet it has to come in and get out in exactly the same time, to the minute. So that's, so it has to hurry up. It has to rush to get out. And by gosh, it does. So I talked about neaps and springs, and these are the springs are the biggies, and the neaps are the littlies,
The babies.
the baby tides, if you like. And here's what happens by and large. Now, there are various degrees of this. The moon can be in different positions relative to the Earth and the sun. But by and large, you're looking at a situation where, it could, I suppose the angle could be anything between 70 and 100 degrees, but for sake of argument, we're making it 90 degrees, where the moon is out here and the sun is out here, and here is the Earth rotating. And the moon going around it. This bulge represents high water on that side of the planet. Now, you'll have to ignore the second moon here for the sake of argument, because the moon cannot be in two places at once, much as sometimes we would like it to be. This is just one part of the month, and this is another part of the month. But just think in terms, there's only one moon there. And you have this bulge, which is high water for that time of day. And you also have the sun. What's happening is the sun has relatively little influence on the tides compared to the moon. The gravitational pull of the moon is what lifts this bulge of water. The sun does it a bit too, but not as much. So this is what gives us neaps. We're just depending on the moon to lift this bulge of water. And as the Earth rotates, that bulge of water travels around the globe. And it can happen, of course, at different times of the month. The moon can be over this side, and it can have an effect. So we also, though, get a bulge on both sides of the Earth.
Planet.
We'll have a bulge on this side, and ignore this first quarter moon for the time being. It's not there to cause this bulge, but the bulge will appear nonetheless. And physicists refer to this as being caused by inertia. I think Kieran Brannigan gave a very good explanation when he suggested that, in fact, it's more caused by centrifugal force. In other words, the spinning of the Earth is throwing this bulge out. I could keep you here all night postulating as to why the two are basically in tune, but it does happen that there's a bulge on the opposite side of the Earth to the moon. And you think in terms of only one moon in each situation, but the bulge is still on both sides. Spring tides, look at what's happening. The sun is up here. Now, it's obviously much higher up there, 90 million miles away, and the moon is always going to be there about, what, 300,000 miles away. But the two of them act in concert. The gravitational pull of the sun reinforces the gravitational pull of the moon, and you get a much higher rise, right? And again, the rotation of the Earth that travels around the globe. We have a word for it, and I can actually pronounce this, and it's CCG, and it's called the period of the spring tides. What CCG means or what it's supposed to represent, I do not know, but it probably comes from the Greek or the Egyptian or something. So different phases of the moon will give you springs or neaps.
Yes.
In other words, different position of the moon relative to the sun and the Earth. Okay? And that's why you get it twice a month. The other thing to bear in mind is that the rotation of the moon around the Earth drags the tides with it. And the moon rises 50 minutes later every day. And guess what? The tides come 50 minutes later every day. There's a couple of other things I think we need to bear in mind, and we're running out of time, about the tides. One is the rate of tide filling and emptying, and there's a little rule, and it's called the rule of twelfths. And unfortunately, I don't have this written down to show you, but it's easily got. Tide rises by 1/12 of its amplitude in the first hour, 2/12 in the second hour, 3/12 in the third hour, another 3/12 in the fourth hour, 2/12 in the fifth hour, and 1/12 in the sixth hour. Now, if it's rising by just 1/12 in the first hour and by just 1/12 in the sixth hour, I think it's a fair assumption to make to say that the tide, the rate of movement of the tide, the strength of the current is at its weakest here. In other words, the current will be slow. It's getting faster in the second hour when 2/12 of that body of water has to move up or down the Irish Sea. It gets even stronger in the third and the fourth hour.
Yeah.
And it's a 12-hour cycle, 6 hours coming in, 6 hours going out. So 2/12 in the fifth hour, getting weaker, and just 1/12, as we said, in the sixth hour, getting weaker again. So in the midway of the tide, as it were, in the third and the fourth hour of the rise of the tide, the current is at its strongest. And then it gets weaker until you get slack water, as they call it. And indeed, the tide does seem to slow down quite a lot, although you'll still notice it if you watch water rising up a dry quay wall, and it's fascinating to see it turn around and start to come down again almost within minutes of it reaching the top of its amplitude. So the strength of the tide varies depending on whether it's rising or falling and what time of the cycle it is at. As I say, it's a 12-hour cycle, give or take 50 minutes, and because it's always 50 minutes later every day. Now, we have a peculiar thing in Skerries, which I'll mention before we finish up, and that is normally in a situation like, say, Dublin Bay, Howth or Dunleary, when they're thinking in terms of the tide, they think in terms of the tide being full on the sixth hour and being emptied or at full low on the 12th hour. And it's running north, coming up the Irish Sea for the first 6 hours as it's filling, and it's reversing direction, it's running south, and it's heading back down the Irish Sea for the remaining 12 hours. Here in Skerries, we do things differently. The tide starts running south about an hour before high tide. So in Dún Laoghaire, if you're watching this and you see the tide suddenly turn and run south, you'll think to yourself, oh, the tide is falling. It's not, it's still filling. The tide in Skerries, and for a large part of the coast around here heading north, is filling from the north as well as from the south. Will be running south because water is making its way through the North Channel around Northern Ireland and forcing its way through a very, very narrow channel. So bear in mind that you can think that when the tide has turned, that it's going to be falling. It's not around here. It's still going to be rising because it's coming in through the North Channel. It's finally forced its way past the rising tide from the south. This is an interesting thing too, which you should bear in mind. When you're sailing with the wind against the tide, the wavy arrow underneath here is the direction of the tide. These are waves, and this is the direction of the wind, and this boat is heading towards this area. When the tide turns, you get a situation called wind against tide, and that basically means the tide is running against the wind. And what that tends to do is whip up waves. You get bigger, shorter, sharper waves. And you can often see this, incidentally, depending on the wind direction, in places like the Sound between Colt Island and Red Island. You stand on the shore there and watch the water as the tide turns. You'll often see quite a choppy little sea being stirred up, and that's being caused very often by wind against tide. And when you sail into a situation like that, especially acute between islands and off headlands where the tide runs fastest, you'll get a very, very choppy ride, and you should avoid it at all costs, really, because it can be very uncomfortable. The reverse is true. When the tide and the wind are going in the same direction, happy days, flat water, good thing. Okay, now I'll finish that there.